In this video, we will show that if we have a commutative ring, then that ring is field if and only if it is simple. So, let us first put the direct part. In the direct part, it is given that R is a field and we have to show that it is simple. So, let us start with any non-trivial ideal of R. Let I be a non-trivial ideal of R. As it is non-trivial, this implies it will at least has one non-zero element. Let P non-zero belongs to I. This implies B inverse belongs to R because R is a field. Now, by the ideal property, we will take an ideal element, that is B, and a ring element, that is B inverse, then the product belongs to ideal, that is B into B inverse belongs to I. But B into B inverse is 1. This implies 1 belongs to I. The moment we have 1 in I, we can say that I is entire R. This implies that is, we have started with a non-trivial ideal and we end up getting it as R only. That is, R has no proper ideals. This implies R is simple. Conversely, we will assume that R is simple commutative ring and we have to show that R is field. That is, we have to show that every non-zero element has inverse. Now, let us start with any non-zero element. So, let A be any non-zero element of R. Now we will generate an ideal out of A. So AI, that is, we will multiply all the ring elements with A. That is the ideal generated by A. That is principal ideal. Now, since A belongs to AR and A is non-zero, this implies the singleton 0 is properly sitting inside AR and R is simple. That means the only choice left for AR is it has to be R. Because it is simple, it has only two ideals, either it is singleton 0 or it is the entire ring. This cannot be singleton 0 because A is non-zero, therefore it has to be R only. Now 1 belongs to R, but R is equals to AR, so 1 belongs to AR. That is, we can write 1 as multiple of A, some multiple of A. So 1 is equals to A into B for some B in R. And since R is commutative ring, we can write it as B also. This implies B is inverse of A. We have started with any non-zero element and we get its inverse. So any non-zero element of R has multiplicative inverse in R. This implies R is